Okay guys, welcome back to part 2 of this short little series. This video I'm going to be talking about how to define circular functions, so sine, cos and tan. Again, we're going to be starting out with the unit circle, which we talked about last video. Basically, this is a circle with a radius of 1, and it's from this circle that we've just defined what radians are. So to recap that, we now know that if we were to travel a distance from here, so the point 1, 0 to some other point on the circle, that total distance, if that's equal to 1, then that angle that line is subtending, or the arc is subtending, is an angle of 1 radian. That's the key result from last video. So let's now talk about the coordinates of a point that is on this circle. So like we discussed last time, just looking at this picture on the left, we're going to use that to understand the picture on the right. From last time, we remember that because this is a unit circle, we've defined it as being a unit circle, the radius of the circle is equal to 1. So that means if we were to take any point on the outside of this circle, let's say its coordinates are x, y, then we can see that the distance from that point to the origin at the center of the circle is equal to 1. We can also see that we've constructed this little right-angled triangle here, and this distance here is going to be x, the x coordinate of this point, and this distance here is going to be y, the y coordinate of this point. So we can see that those two values actually correspond to the two sides of this triangle. So if we're looking at this triangle as a triangle, and we know that this angle here is some angle theta, we can then use this to figure out what the coordinates of this point are. So what we can do to start off with here is we can remember that, using our knowledge of SOHCAHTOA, which is how we've defined sine, cos, and tan in previous years, which is just the ratio of the opposite to the hypotenuse is equal to sine. We can say, okay, if we look at this little triangle here, we can see that sine of this angle theta is going to be equal to its opposite, which here is y, divided by the adjacent, which is equal to 1. And we can see here, well, y divided by 1 doesn't really matter what y is. Is just going to be equal to y, isn't it? Because y divided by 1 is just equal to y. So therefore, we can see that sine is equal to y, and similarly, cosine of theta is going to be equal to adjacent over hypotenuse, which will be x divided by 1, which will just be equal to x. So therefore, we can conclude from that the coordinates of some point, any point around the outside of a unit circle, are just going to be equal to cos theta, sine theta, where theta is this angle in the center over here. All right, so using this newfound fact, we can then make some more derivations. So for example, we can see, well, what is the ratio of the other one? You remember, we have sine, cos, and we've also got tan. Well, the ratio tan is defined as being the ratio between the opposite and the adjacent. So tan is opposite over adjacent. In this case, that is y over x. What can we do with that piece of information? Well, if we have a think about it, to start off with, we can see, well, we now know that y is equal to sine and x is equal to cos, so we can rewrite this ratio here to say that tan theta is going to be equal to sine divided by cos. This is a really useful ratio that we are going to be using throughout the exercise. We can also see this as a ratio of two similar triangles. So we can see the number tan theta, that is just a number. It's going to be exactly the same as tan theta divided by 1. So therefore, if we were to have a triangle like this triangle that we have drawn on here, which has a ratio between its opposite and its adjacent sides of sine over cosine, that triangle would be similar to a triangle with corresponding side lengths of tan and 1. That's just using our knowledge of similar triangles. So what we mean by that is if we were to make the distance of, the side length of an adjacent side of a triangle equal to 1, and then build up a triangle like this, such that that triangle is similar to this other triangle. Remember, similar just means the angles are the same and the ratio between the side lengths are the same. We can see this larger red triangle is similar to the black triangle because they both share the same angle theta. We can then conclude that the opposite side of this triangle is going to be equal to tan theta. So that's everything in this image on the right here, just sort of put into some perspective. So let's just take a break here and see how we can use this result to make sense of some things. So first up, if we were trying to evaluate the ratio sine 3 pi on 2 specifically, let's think about what that looks like in terms of a triangle. So first up, we've already found out that sine is just the y-coordinate of a point on the outside of a unit circle. So where is this point 3 pi on 2? Let's just quickly draw a circle. So remember from what we looked at last video, the points on the outside of a circle like this are going to be 0. This one will be pi on 2. That's going to be pi. That's 3 pi on 2. And this is 2 pi, the points around the outside of a unit circle. Those are the corresponding radians. So here we're looking at 3 pi on 2. So what that means is we've started here, we've rotated 3/4 of the way around the outside of the circle, and we're at this point right here. And remember, sine is the y-coordinate of that point. So what is the y-coordinate of this green point down here? Well, of course, that's equal to 0, -1. Like the coordinates of that point are 0, -1. So therefore, the y-coordinate of that is -1. That's the answer there. Let's try this next one. So cos 5 pi on 2. Let's just quickly draw a circle, just like before. Where is this angle, 5 pi on 2? Well, if we were to start here at 0, we could go, okay, that's pi on 2, that's pi. What is 5 pi on 2? Well, 5 pi on 2 is the same as, well, how many times does 5 go into 2? It goes in twice with 1 remainder. So this is the same as 2 pi plus pi on 2. So let's make one full rotation. That's our 2 pi. And then let's do 1/4 rotation, which puts us here. So we can see that that point there is the same as a pi on 2 rotation, which is also the same as 2 pi plus pi on 2. Because if I go all the way around the circle and then go pi on 2 radians, that puts me at the same position as if I had just gone 2 pi radians to start off with, right? Notice that when I'm writing these, I don't need to write the radian symbol. We're just going to assume that whatever you've written in the brackets is in radians unless you put a degree symbol. That's really important to note. If you don't see a symbol in there, just assume it's in radians. If there is a degree symbol, it's in degrees. Otherwise, just for all intents and purposes, it's always in radians. But yeah, we can see that this point here is the same as cos 2 pi plus pi on 2. And of course, cos, like we saw up here, is actually just the x-coordinate of a point somewhere on the unit circle. So what is the x-coordinate of this point in green here? Well, the x-coordinate of that point is just going to be, well, what is that point? That point's 0, 1, isn't it? The x-coordinate is equal to 0. Yeah. So therefore, the x-coordinate of this point is equal to 0, and therefore cos 5 pi on 2 is equal to 0. Okay, a couple more. So sine -3 pi on 2, where is that on the circle? Well, negative means start at this point here and rotate backwards. So I'm going to rotate back 3 pi on 2 units. That puts me right here. Now, what's the y-coordinate of that point? Because remember, it's sine, so we're dealing with y-coordinates. The y-coordinate of that point is equal to 1, so therefore the answer over here is equal to 1. And then lastly, let's think about tan. So tan is a little bit trickier. So remember, tan is the ratio between sine and cosine. So let's first figure out where we are on the unit circle. So 55 pi's. That's a big number. We're going to be rotating a whole bunch of times around this circle. How many times? Well, it actually doesn't really matter, does it? Because if we were to think about this, if we start here and rotate 2 pi radians, that puts us here. if we were to rotate 4 pi radians, it puts us here, 5 pi, 6 pi, 7, 6 pi, 8 pi, 10 pi. If there's an even number of pi's, we're going to be ending up, or an even number of pi radians, we'll end up over here. If it's an odd number of pi radians, we're going to end up over here. So we can see this is an odd number of pi radians, so this is just going to be the same as tan of pi. So we're going to be ending up right here on the unit circle. So tan is the ratio of sine to cosine. So that is sine pi divided by cosine pi. So what is sine pi? Sine pi is the y-coordinate of this point. So this point here is the point -1, 0. So the y-coordinate of that point is 0, and the x-coordinate of that point is -1. So 0 divided by -1, that's equal to 0. So therefore, tan 55 pi is equal to 0. Okay, so the next couple of things we need to understand. So jumping off of this information, we need a few key angles that we can work with. So the useful thing about the unit circle is that we can create similar triangles from the unit circle. If we know something about the unit circle as it relates to the angle of 30 degrees, we can then scale up that triangle, and it's going to be the same ratio between the opposite and the hypotenuse sides as any other triangle with that ratio. So if we can make some realizations about some simple triangles that we can know everything about fully, we can then apply those same realizations and those same facts to any other triangle that has those same angles. So let's start out with this equilateral triangle over here. This is an equilateral triangle with side lengths 2, 2, and 2. So that line there just means that all of the sides are the same length. What are the angles that are enclosed within this triangle? Well, we should know that all of the angles inside of a triangle need to sum up to make 180. 180 divided by 3 is equal to 60 degrees. So that means that each of these angles is the same. They're all equal to 60 degrees. So let me just put that in there. All the same angle. Now, if we were to take that triangle and slice it in half, so I'm going to draw a line down the middle like this, that's going to create a 90-degree angle over here. Remember, we can only really use these trigonometric ratios if we have 90-degree angles. And that means that that angle at the top got sliced in half, so it's now 30 degrees. So the side lengths of this triangle were 2, which means this distance from here to here is 1. And we can figure out what the other distance is here, the one that's opposite the 60-degree angle, by using Pythagoras' theorem, which says that the sum of the two smaller sides is equal to the sum of the squares of the two smaller sides is equal to the square of the hypotenuse. So therefore, we can say that 2 squared is equal to, well, this unknown side, right? This unknown side, let's call it x. X is going to be equal to the square root of 2 squared minus 1 squared, which is going to be equal to the square root of 3. So this side length here is root 3. Now that is an extremely useful result. For example, if we wanted to know what is cos 60 degrees equal to, right? So cos 60 degrees. Now every single triangle in the world that has a 60-degree angle in it, any right angle triangle that has a 60-degree angle, is going to be similar with this triangle that I've just sketched here. Now, we know everything about this triangle that I've just sketched here. We know all of its angles, we know all of its side lengths. If we look at this triangle, we can see that cos 60 degrees is equal to adjacent over hypotenuse. Now, the side that's adjacent to 60 degrees is 1, and the hypotenuse is equal to 2. So therefore, cos 60 degrees is equal to a half, and this is always going to be the case. Similarly, if we wanted to know tan of 60 degrees, that's going to be equal to opposite over adjacent, so that would be root 3 over 1, so that would be equal to root 3. And similarly, we could deduce anything we wanted about sine, cos, and tan of 30 degrees and 60 degrees. Okay, so that's the first useful result. The second special triangle that we need to understand is if we take a square of side length 1 and we cut it along the diagonal like this, so cut it along the diagonal like that, we're going to create, no, that's not very pretty, There we go. We're going to create a right-angled triangle with a 45-degree angle on either side. Because, of course, 90 divided by 2 is equal to 45, because I've cut this in half. The side lengths over here are 1 and 1, and similarly as to before, we can use Pythagoras' theorem to work out the other side length here. So c squared is equal to 1 squared plus 1 squared. Square root both sides, we can see that c is equal to the square root of 2. So that's this side length over here. And just like before, we could then work out what is, for example, sine of 45 degrees. Well, sine of 45 degrees is equal to, if we look at this triangle, 1, so the side that's opposite over hypotenuse, 1 over root 2. And then we could rationalize the denominator by multiplying the top and the bottom by root 2 to write this in the form root 2 over 2. So that's the first thing we need to know about these special triangles. And of course, we should remember that 45 degrees, that's the same as pi on 4 radians. In fact, let's put this in a little key somewhere. So some other things that you really need to know is that, also note, let's say, 45 degrees is the same as pi on 4 radians. 30 degrees is the same as pi on 6 radians. And 60 degrees is the same as pi on 3 radians. And of course, we also should know that 90 degrees is pi on 2 radians there. Conversions that you should just know off the top of your head. Finally, the other thing that you need to understand is symmetry properties. So we've got this little diagram here. It's a little bit hard to understand when it's written like this, but the general gist of it is that if we were to create a triangle over here, right, that triangle there would be symmetrical to a bunch of other triangles. So for example, we can see that this point over here has the same y value as this other point over here. And it has a negative of its x value over here. Now, what is this point over here? Well, it's the point that is equal to this angle here, taken away from this half circle. So we know that that half circle is pi radians. If we go pi radians and then we go back that angle, go back this angle, theta, we're going to end up at a point that is pi minus theta. That point there will have the same coordinate b as that other coordinate, and it's going to have the negative of a. So therefore, the coordinates of this point would be negative a, b, which tells us, for example, that cos of negative a is going to be equal to, well, cos of negative a, that's the x-coordinate of this point over here. The x-coordinate of that point is negative with the x-coordinate over here. So that's going to be equal to negative cos a. The y-coordinate, so sine of negative a, is actually the same between those 2 points, right? Or sine of, sorry, what I'm writing doesn't make any sense. Let me go back a little bit. So, cos of pi minus theta. Let's go back to this. So this angle, pi minus theta. Cos of that angle is equal to negative of cos of pi, because it's the negative x-coordinate of that point. So it's negative cos of theta, that angle over there. And sine of pi minus theta is going to be equal to sine of theta. It's the exact same, because the y-coordinate of this point is the same as the y-coordinate of this point. By the same token, if we were to consider, say, for example, this point over here, which has an angle of 2 pi minus theta, so we've gone all the way around the circle and we've gone back to there, we can see that that point has the same x-coordinate, but the negative y-coordinate as this point here, p theta. So in that case, for example, sine of 2 pi minus theta will be equal to negative sine of theta. Don't worry too much about that diagram. It is really confusing when you first look at it, but it does kind of make sense when you think about it. think the best thing to do here is to just jump into a few examples, and then hopefully we can wrap our head around what's going on. So first up, what is cos of 5 pi on 4? So first up, we need to work out where on the unit circle are we right now. Where on the unit circle are we? This is the unit circle. It's a terrible circle. Slightly better. Now, 5 pi on 4. How many times does 5 go into 4? Well, it goes in once with some remainder. So we're going to be somewhere over here in the third quadrant, right? So that point there, this angle that we're forming here, is an angle of, will be pi plus pi on 4. Yeah? Because 5 pi on 4 is equal to pi plus pi on 4. Okay. So let's rewrite this question then. We can say that what we're trying to find here is cos of pi plus pi on 4. So we could just look at this diagram and use the symmetry property to work out what that's equal to, but let's just try and understand it first. So here's this angle here, pi on 4. Okay, so we know, looking at that triangle there, or that point on the circle here, that point is going to be symmetrical to this point over here, where that angle there is pi on 4. Okay. So based on our special triangles up here, we can see that that angle there, that's pi on 4, that's a side length of 1, okay? Well, what is cos of pi on 4? So cos of pi on 4, cos of 45 degrees, is going to be equal to, let's think about this triangle up here, it's going to be equal to the adjacent side, so 1 over root 2. And like we said before, 1 over root 2, that's just the same as root 2 over 2. So this is root 2 over 2. Now let's think about that point there. That point is the negative of this point over here. So again, we're looking at cos, which is the x-coordinate of this point here. The x-coordinate of the point in the first quadrant is the negative of the x-coordinate of the point in the second quadrant, because it's, on the other side of the y-axis. So therefore we can see that this point here is equal to negative cos of pi on 4. That's one of these symmetry properties. And therefore that is equal to negative root 2 on 2. So that should be the answer for this first one. Okay, let's move on and consider the second one. So here we have sine, so we're dealing with the y-coordinate of a point on the unit circle. So again, let's just draw the unit circle. Every time you're going to be doing the same thing. Let's consider where is this point firstly. So 11 pi on 6, that's the same as going all the way around the outside of the circle. So 2 pi radians minus pi on 6, because 11 is 1 off of 12. So we can see that 11 pi on 6 is the same as 2 pi minus pi on 6. So that means that we're over here right now, right? We're at this point here, and we're interested in its y-coordinate. We want to know what that is. So that little triangle there, again, it's not a very good picture because it's not really well drawn, but we can see it should be symmetric with another point right here. Yeah, we'll just leave that. That's okay. Okay, this point here, let's suppose that that's a 60-degree angle, but it's not a very good diagram, but let's say that's a 60-degree angle, that's pi on 6, that's pi on 6. We're interested in the y-coordinate of that point. So let's consider our triangle that has a 60-degree angle. That's this one over here. I'll redraw it for us over here. So that's our pi on 6, 30-degree angle up the top there. We know that that side length there is 1, that side length is 2, this one's root 3. So sine of an angle is the opposite over a hypotenuse. So therefore this is 1 over 2. So we can say that firstly, this angle here that we've drawn, that is the negative version of the point that's in the first quadrant. So this is going to be negative of sine pi on 6. And looking at this special triangle, we can see that pi on 6 is a half. So therefore the answer over here is going to be equal to negative a half. Let's try another example, this one over here with cosine. So cosine 200 pi over 3, again, that looks like a big scary number, but we just need to work out, what's the remainder? That's what we really care about here. So we can see that 200 goes into 3 with how many remainder? Well, if we were to try and divide 200 by 3, so let's do how many times does 200 go into 3? We could see that, all right, 3 goes into 2 0 times, 3 goes into 26 times with 2 remainder, and then 33 goes into 6 into 20, 6 times with 1 and with 2 remainder again, so therefore the remainder is going to be 2. So all that is to say, this is going to be equal to 65 pi plus, or 66 pi plus 2 pi on 3. That should be the case. Yeah, so an even number of pi's plus 2 pi on 3. So that should actually position us, if we do an even number of pi's around the outside, so we just come back to here, and then we go 2 pi on 3, that's going to position us over here in the second quadrant. So we're over here in this quadrant right here. Okay, so if we're in that quadrant there and we're interested in the x-coordinate, we can see that that is going to be symmetric with this point over here, which is pi on 3. So this here is the exact same thing as cos of 2 pi on 3, which is the same as cos of pi minus pi on 3, which is the same as, like I said, it's the negative of that value over there, so it's negative of cosine pi on 3, which means that this is negative. So let's refer to this triangle up here, pi on 3. Okay, so pi on 3 is the 60-degree angle, so this is adjacent over hypotenuse, so that's root 3 over 2. So this should be negative root 3 over 2. All right. So that's how we do that. All right, let's move on and consider some tan examples. So this first example here, we're trying to deal with 26 pi over 3. So again, let's just write this in terms of its number of pi's. So this is going to be tan of, okay, so what's the closest multiple of 3 to 26? So we can say, all right, we know that 3 times 8 is equal to 24. So therefore, we would say this is equal to 8 pi plus 2 pi on 3. 26 pi over 3 is equal to 8 pi plus 2 pi over 3. So that's an even number of pi's again. This positions us in the same quadrant as before. So again, we're over in this quadrant over here. Okay, and we're dealing with tan. A really useful little acronym for you to use just to make this process a little bit faster is this acronym CAST, which we can remember as all stations to center, CAST. This is just basically the letters for the particular value of sine, cos, or tan, which one of them is positive in that quadrant. So in the first quadrant, all of them are positive. In the second quadrant, sine is positive and cos and tan are negative. So therefore, tan is negative in this quadrant. So that just tells us that this answer is going to be equal to, so firstly, that's the same as 2 pi on 3, right? Tan of 2 pi on 3, which is the same as pi minus pi on 3, right? That's going to be equal to the negative of tan of pi on 3. Okay, so negative, and I know I've run out of space, but let's just do it over here on the side here. So equals negative tan pi on 3. That's right, I'll squeeze it in. So tan of pi on 3, if we go back to our triangle here, so pi on 3, that is the 60-degree angle of this triangle here. So tan is opposite over adjacent, so it's root 3 over 1. So the answer here should be negative root 3, and I know it's really cramped down there. Okay, so let's just jump ahead a little bit. All right, so that's, I think, enough for us to get a feel for how the unit circle works. Basically, my advice here is draw a unit circle to work out which quadrant you're in. Draw a right-angled triangle to help you out. I guess we'll just do one more really quickly. So this one here, this is negative 45 pi on 2. All you need to know looking at this is, firstly, we're dealing with a negative there. So we're rotating around the circle like in this direction. Again, just use a diagram like this to help you visualize it. So if we were to rotate, this would be pi on 2, that would be pi, that would be, that would be 2 pi, so negative tan of negative 2 pi would put us here. So where are we, basically? Are we up the top or are we down the bottom is our question. We can see that obviously 45 is a even number. 45 is divisible by 3, so therefore we could write this as tan of negative 3 times 15 pi on 2. Are we at the top or down the bottom? Yeah, it's a tricky one. It doesn't matter. It doesn't really matter, does it? So in the case of tan, regardless, we know that we're either up here or down here. When we're dealing with tan of either of these angles, they're going to be equal to the same result because tan is equal to sine over cosine, right? And of course, sine at each of these 2 points, one of them it's equal to 1, one of them it's equal to negative 1. Cos is equal to 0, so if we're dividing by 0, this is going to be undefined no matter what. So this is just undefined. Okay, and then finally, we could do this on the calculator because that would be too hard to do in our head, or using a pen. So tan of 1.3. Let's do that over here on the trusty CAS. If we're doing 1.3, it's really important that we make sure, was it 1.3? Yeah, 1.3. Make sure that we're dealing with the correct units. So in this case, there are no units given to us in this question, so we just assume that it's in radians. So we need to make sure that our calculator says radians right there. Hit execute, and it says that's approximately equal to 3.6. So 3.6 is what that ratio is. All right, beautiful. Let's move on. So another quick couple of examples just to make sure that we understand symmetry properties. If sine theta is equal to 0.6, we need to find a few things. So let's just see if we understand what we were talking about back up here with the symmetry properties before we wrap this little video up. So if sine theta is equal to 0.6, then that means that the angle theta is the angle such that the y-coordinate of a little triangle that we draw over here, the y-coordinate of that, which is the height, is equal to 0.6, right? So now the question is asking us, what is sine of pi minus theta? So pi minus theta is going to be over here. That is to say we travel pi radians around the outside and then back theta. So that puts us right here on that little triangle. We can see that that triangle, or that point there, that's at that position on the unit circle, has the exact same y-coordinate as the one in the first quadrant over here. The y-coordinates of those 2 points are going to be the same, which tells us that this identity, sine pi minus theta, is always just equal to sine theta, and that's always true. It's one of the symmetry properties. So that means that if we know that sine theta is equal to 0.6, then sine pi minus theta is also equal to 0.6. Let's have a look at this next one. So again, draw a unit circle. All right, now this point here, that's in the first quadrant, we know sine theta is equal to 0.6. So sine pi plus theta, that's going to be the point on the unit circle that's over here. That's pi plus theta. So this is theta. This is pi over here. Looking at that point, we can see, again, we're interested in the y coordinate at this point because we're looking at sine. That has a negative y coordinate compared to the symmetrical point in the first quadrant. So because the y coordinate of this green point is negative of the blue point up here, we can see that sine pi plus theta is always equal to negative sine of theta. And given that we know that sine of theta is equal to 0.6, we can say that this is equal to negative 0.6. And then one more, let's just use the same triangle as that last example to help us out over here. 2 pi minus theta is going to position us at this point over here, right? Because 2 pi is one full rotation around the circle, and then minus theta positions us here. So this is a point with an angle of theta. We can see that the y coordinate of that red point is the negative of the blue point up there. So this is going to be equal to negative sine theta, like with the other example, and therefore this is also equal to negative 0.6. So similarly, if we were dealing with cosine, and over here we're looking at degrees instead of radians, that's why there's a degree symbol. Remember, if there's no notation, just assume it's in radians. This time it is in degrees. Regardless, though, we're trying to find the symmetry properties as they relate to cosine for this question here. So we do the same thing. We would first draw a little circle. We'd try and work out where we are. So the information that's being given to us is that if this angle here is x degrees, then cosine, which is the x coordinate of a point, is equal to 0.8. So that's the distance from here to here. That's 0.8, the x coordinate of that point. So we're now considering a point that's in the second quadrant. So that's 180 minus x. So that's putting us right here. So we want to know what is the x coordinate of that point. We can see that that's just the negative version of this first diagram here. So we can see that that's going to be negative cosine of x degrees. And we know that cosine of x degrees is just equal to 0.8. So this is equal to negative 0.8. Next example, let's quickly draw it before my battery runs out and the computer dies. This is 180 plus theta. So again, we know that this one over here is 0.8, that's x. 180 plus x is going to put us just over here, so that's x. We want to know what's this x, the x coordinate of that point there. So what's that coordinate? What's that distance there? Again, that is the negative version of 0.8. So we can see, again, that's going to be negative cosine theta, which means this is equal to negative 0.8. And then as for the last example, let's just draw another circle over here. Let's not be lazy. That's x. That's 0.8. Okay, we're interested in that. We know that. We know that we're looking at this point here. So negative x degrees means start at this point here, rotate x degrees this way. So we've now created an angle of x over here. We can see that that point in green has the exact same x value, the exact same x coordinate as our initial value of 0.8, which means that this is the same. It's the same value. So cos negative x is equal to cos of x. That's another one of these symmetry properties, which means that cos negative x is also equal to 0.8. All right, hopefully me going through this has sort of helped you. Please let me know if you have any other questions. Send some questions my way and I'll help you out with them. And yeah, I'll see if I have time to make some more videos on this topic. Otherwise, I'll see you guys in class.